In this video, we're going to go over through torque, one of the most important concepts in physics. In just the first few minutes, you'll find out all the equations that you need to know and where they come from. These will be the equations for torque, moment of inertia, and the second Newton's law in the rotational reference frame. In the next few minutes, you will also find out a step-by-step instruction, so a method for approaching any torque-related problem. This will be especially useful for people who right now are looking at these problems and they don't even know where to start. I will give you a guidance, so a step-by-step guide on how to approach any problem, no matter what the question is asking. Finally, in the rest of the video, we're going to go over a really quick practice problem to see how those steps that we just learned apply to solving real-world problems. So let's start by firstly analyzing our equation right here. So torque is essentially our rotational equivalent of force. The equation for it is going to be torque is equal to perpendicular component of the force times distance away from the point of rotation, or force times distance times the sine of theta, which is the angle between the axis of rotation and the force. Now, what does this actually mean, right? So let's say very simple example of a torque. Let's say, for example, you are rotating a door and you're applying a force that is like this, but it's at the angle. This force, as we already know, is going to have a perpendicular component, right, and a parallel component. I have a question for you. Which of these components, this one or this one, is actually going to rotate this door? So hopefully you said that it's going to be the perpendicular component, right? Because you have to push the door in this direction in order to actually make it rotate. This component is not going to contribute whatsoever to rotating the door itself. So this is what I mean when I say it's the perpendicular component of the force times the distance away from the point of rotation. And the point of rotation in the case of the door would be here. So the distance here would be the distance from this point of rotation, so the wall in this case, all the way to where the force is applied. We could also write this in terms of sine. So in this case, the angle, right, is the angle between the thing that is rotating, so the axis of rotation, and the force that is being applied. So right here, this is the theta. Which is just going to give us the perpendicular component, right? Because this is just f sine theta. Now, let's take a look at the next new topic that we have here, which is the moment of inertia. Moment of inertia is a rotational equivalent of mass. Its formula is some kind of constant, so some kind of number times mr squared, where m is the mass in kilograms and r is the radius of the object in meters. Now, moment of inertia doesn't have any special units, so since we're multiplying kilograms times meters squared, those are going to be just the units. Now, this constant thing is probably confusing, right? Because what does this actually mean, the constant, and how do you know it? Well, different shapes are going to have different moments of inertia. So for example, a cylinder will have a formula as 2/5 mr squared, but a sphere will have a different number in the front here. So you don't have to memorize these numbers. You will most likely be given these formulas either in the separate formula sheet on the exam or in the actual problem itself. But I just want you to keep in mind that the moment of inertia is mr squared, and then there's some kind of number in the front here. Finally, we have also a second Newton's law in the rotational frame of motion. So as you remember, the second Newton's law is net force times mass times acceleration. So we just plug in all our rotational equivalent for it. The net torque is equal to moment of inertia times rotational acceleration. So what we have here is, if you've noticed, we have now two equations for the torque. This one, which is I times alpha, and also this one, which is force times distance. So we can combine those two equations into one to get our final equation, right? So we're essentially connecting, right, the forces to moments of inertia. Finally, just one more thing I want us to keep in mind is that we can convert all our linear quantities to angular quantities, or the other way around, by multiplying them by the radius. So for example, you can get the linear velocity by multiplying angular velocity by the radius of rotation, right? Or you can get the linear displacement by multiplying angular displacement by the distance, or same thing with the linear acceleration and rotational acceleration. Now, let's really quick look over our method for approaching torque related problems, right? So what I'm going to do is I'm going to take as the base, I'm going to take our method for approaching second Newton's law problem. So if you already are an expert in the unit of forces, right? What we did there essentially is first we started any problem with just drawing a free body diagram. On that free body diagram, we calculated or we showed what forces are present here, right? Tension and mg force, etc. We labeled these forces, right? And we choose a coordinate system. Now, if we talk about the torque, the clockwise rotation is typically considered negative and counterclockwise is positive, right? So those are all the steps that are already well familiar to us from the unit of forces. Now, the additional steps here is that we have to identify a rotational point. So in the case of the door that I just showed you, it's pretty obvious, right? What is the rotational point? It was just right here around the door. But in some cases, let's say if the object is now rotating, you can pick whatever moment you'd like as your reference point. So from the reference point, from the rotational point, you can note the distances of each force, right? Because you'll need that later to calculate the torque, which is force times distance. Great. Now you'll apply the second Newton's law in the x and the y direction. So again, those will be the same steps we had in the units of forces. We'll label our net force in the horizontal direction, our net force in the vertical direction, and set them equal to either 0 or ma. But in addition to our two equations, second Newton's law in x and y, or sometimes it's only one of those, right? Only the horizontal, only vertical. We will also set up the rotational motion. So we'll calculate the torque of each force and set up the second Newton's law in rotational reference frame. So basically write down this law and add up all the torques and set them equal to I alpha, or where the alpha is 0, right, if it's not rotating. So essentially we're adding one more equation over here to our method for solving force related problems. Great. So now let's take a look at, okay, just to conclude this, right, we essentially will have three equations, right, and whatever the question is asking, we can solve this by combining these three equations together. So let's take a look at how this method applies to our next problem right here. So here we have a seesaw that is 4 meters long. So let me just redraw it really quick. So a seesaw that is 4 meters long and is balanced at a midpoint on a fulcrum. So one child of mass 25 kilograms is at one end of the seesaw. To balance the seesaw, another child of mass 30 kilograms wants to sit on the opposite side. Your task is to calculate how far from the fulcrum the second child needs to sit to balance the seesaw perfectly, making it horizontally at stationary. So what they're saying is basically, right, that the object is not accelerating, it's not rotating, right? So linear and rotational accelerations are 0. So now that we draw our sketch, let's draw a free body diagram on this object. So guys, we always draw the free body diagram for the thing that should be rotating. In this case, it's the seesaw. So the seesaw is experiencing three forces. I want you to think what those three forces are. Well, one force is the force of the child on the left. The second force is the force of the child on the right. And of course, there is the normal force from the fulcrum, right? From the fulcrum support. So the second step, now we have to consider the distances away from the moment of rotation. So the point of rotation here is pretty obvious to pick, right? It's just this fulcrum right here. It says it sits all the way on the left end. So it's just going to be, so the distance this force is applied away from the moment of rotation, the point of rotation is going to be 2 meters. Just half of the length of the seesaw, right? So 2 meters right here. This one is unknown, so x, right? And the normal force N, since it's applied at the point of rotation, right? Its radius is 0, right? Since it's at the point of rotation, is the distance of 0 away from where we're rotating. So let's write down our equation for the torque. Net torque is equal to, in this case, net torque is equal to 0 because we don't want the seesaw to rotate. Now, let's take a look at all the torques that we have here. So we have this force times this distance. By the way, side note, right? Do we have to worry about the angles in this case? The axis of rotation is here and all the forces are applied perpendicularly to it, right? So at 90 degrees. And sine of 90 degrees is 1. So we don't have to worry about the angles. The torque in this case is just going to be force times distance. So torque of the first one is going to be m1g times distance away, 2, plus normal force times distance of 0 away, so essentially this term cancels out, minus m2g times x is equal to 0. Now, why is this one minus all of a sudden, right? This m1g makes the object rotate in a counterclockwise direction, so it's positive torque. This one, on the other hand, makes the object rotate in a clockwise direction, so it has a negative torque, right? If you kind of have a problem to remember which one is positive, which one is negative, as long as you establish one of them is positive and one is negative, it's okay, right? You can pick your own reference frame, remember. Now, we calculating x, so m1g times 2, rearranging for x, g cancels out on both sides, so it's 2 times m1 over m2 is equal to x, or if we're plugging all the numbers, m1 is 25, m2 is 30, so x will be 1.67 meters. And just like that, we solved our first torque problem. Now, in the next video, we're gonna keep going over problems that are a lot more involved and a lot more complicated for torque. So make sure that you watch those videos if you want to do well in this unit, and make sure that you practice solving these questions on your own. Thank you guys for watching. As always, keep practicing and keep watching these videos on your way to an A. Thank you.